And now if I execute here, we have a sample room, and if I redo it, we have another room. So this is really the shape generator that we want to create, is the ability to generate rooms filled with specific primitives like spheres, cubes, and a bunch of stuff. This is super useful, especially if you are into 3D machine learning and you want to develop very quickly data augmentation mechanisms, or you want to train an entire model only using synthetic data without actually going on the field and taking the data with laser scanner, photogrammetry, a drone, LiDAR, whatever. So the workflow for that is super dead simple. We are going to first delineate what are the basic shapes, which can be a plane, a sphere, and then we will assemble them into a room, add labels to each of these elements so that we can leverage what kind of shape it is and which primitive it belongs to. And after that, we are ready to export that as a PLY. Again, if you watch the tutorials of 2 weeks ago, this is super handy because this is actually making sure that you can develop an entire pipeline end-to-end without leaving the comfort of your chair. Based on that, what is also very, very cool, and this is what I highlight here, is that you don't have a ceiling to how many room variation you want to generate. You can have 3 or 5,000. The human needs that you will inject, or the time needed, will be the same if it's automated in the right manner. And what is good is that I give everything to you, so the code, you will have access to that, the data and so on, and you will see that at the end of the video. So let's dive right onto the workflow and how we can create that using only Python. Right, so the toolbox is that simple. As always, I really love to make sure that we tie down only what is necessary. We are going to use right now Python and Anaconda. I have other videos if you are a bit unsure about where to start, how to set that up. With that in mind, actually, we are going to use the terminal command to activate a specific environment, and in it you install NumPy, Matplotlib, Open3D, and the GitHub repo that I give you at the end of this tutorial. Note that in here you may also want to install your preferred IDE. I will be using Spider, but you can use any that is fine with you. So the workflow, as I mentioned before, is that simple, and we'll move on to 13 stages. Let's start with stage 1, environment and setup. I'm super happy to say that pre-order and already digital version of my new book, 3D Data Science with Python, is already available. This is with my favorite publisher, O'Reilly. Fantastic team. 18 chapters to have everything from workflow, code, templates, and everything. So it's available on O'Reilly and also at Amazon.com or in your local Amazon distributor. You can already pre-order now, paperback or Kindle. Beautiful. So before doing anything, I will just make sure that this is my console directory. And as you can see through environment and setup, I import only NumPy as NP, Open3D as O3D, OS, and Matplotlib if we want to export images. So I execute that. Now we can move on to stage 2, creating our 3D visualizer. The idea here is very simple, is to make sure that at each stages of our workflow, in 13th step, if you remember, we have a way to verify, qualitatively at least, what we are doing with our specific functions. And for that, we are going to develop this visualize point cloud function that takes in points, point list, labels, also an array. And if we want to show in 3D the UI or save an image, and this is what we have. And as you can see, I will make sure that the labels are tied to a color map, 0, 1, 2, 3, 4, for undefined, horizontal, vertical, spherical, and cubes, so that we can attach specific colors for rendering, right? So this is all that I do here, and my function is now defined. Beautiful. Time to move on to stage 3, generating horizontal planes. If you remember from the previous tutorial, I developed this viewer, and in it you have this shape generator. And what it can do, it's online, you can access it through learngeodata.eu. You can add cube, spheres, cones, a cylinder, and a lot of stuff and export that. The idea here is reuse the same principle. How do we generate their shapes? Essentially, it's a mathematical equation that we translate into a surface, and then we'll sample it to have the point cloud from there. But of course, if we only sample it on the surface, we will have something that is dead perfect. And what we want to have is some kind of noise that would simulate, in a way, conditions that are not perfect. This is super important. So if I get back to the code, as you can see, my function takes in some parameters that are linked to the mathematical equation of a plane. What I will be using here is the center, the width, and the length of the plane. And then the point density is really only about how many points you want to have sampled onto these specific planar shapes. And after that, the noise level is really how much variation you want to have for a point, within which range you want it to be able to vary alongside this planar distribution. So in here, it's simple. I calculate the number of points, I create the grid, I create flat points with a constant, and then I add the noise with the random normals. From there, I can add the labels to my array, and I return both points and labels. And after that, to test it, as I mentioned, I always like to test it when I code. I will create the center, and I will retrieve my flow points and labels, and based on that, we can visualize. So if I execute this, you can see that we have our Open 3D view, and we have a very nice planar shapes that is generated. So this works beautifully. Stage 1 is done. Congratulations. From there, we can move on to stage 4 for vertical shape generation. In a very similar fashion, we generate vertical planes. But of course, here, as you can see, our mesh grid is a bit different, and the orientation as well, because we want to flip it. So that's what we are doing here. After that, I define another center, and I extract from the center and the parameter width and height and orientation my wall. So let's visualize. As you can see, we really have something that is vertical, so it looks like it's working. And also the width is not as big because we want to generate a room. So here we have a plane for the base and maybe the ceiling, and we have the ability to generate vertical planar shapes for the walls. Nice. Let's go on to spherical shape generation. Now, this is not a necessity for a room, but I wanted to show you how you can do spherical shape generation, because this is something that you may encounter in your coding or professional experience. So as always, I take in the center, the radius, and there's two other parameters. So the only thing is I have this polar to Cartesian coordinates transformation to make sure that I can create my sphere. And this is really, well, the area that we will be needing. And after that, all that we do is really reuse these parameters, and beautiful, you have a sphere. And you can see that if I rerun it, I have a distribution that is really different. Okay, almost there. Step 6 is cube shape generation function definition. Okay, so what about generating a cube? This is also something nice, and yeah, actually a cube is more or less, in a way, you could create the cube by assembling the horizontal or vertical planes. But what I do here is a bit different. I create a grid based on various faces, calculate the coordinates, and then after that, I will make sure to add random noise. So this is a bit different than what we did before. You can also leverage some primitive generation function that you have in Open3D and then sample from that. This is also to show you that you can just give a cube center and a size, and that will generate for you the cube as seen here. And again here, if you want to have more density, right? So let me take point density parameter. Right after that, if I were to put 1000, sorry again, I will put that, and yeah, you see that you have 1000 points. Okay, that's working. Now let's explore the remaining elements. Beautiful. Now stage 7 is creating random noise. Yes, we have our various shapes, but what I like to do also to complicate a bit the various experiments that we do after is generating random noise. And for that, because we are in this specific scenario where you want to generate rooms, 3D point clouds of rooms, you want to make sure that the noise really fits within the bounding box of your room. So room min, room max, and the number of points that you want to generate. And of course, the labels of the noise, if it's not 0, you can put something else, but here it is 0. This is all that I'm doing. And again, using the random uniform, sample that based on a Gaussian distribution, which is usually the best way to move, because real world instrument, when they're well calibrated, you don't have systematic error. Usually the measurement accuracy relates to Gaussian distribution, so random normal distribution. So let me execute, and you see that we have random noise that is generated. Beautiful. All right, and 8 is generating a simulated training data set. It's time for us to generate our simulated training data for further experiments. Here, it's a large function. I will not detail everything. Again, you have the link to the repo with the GitHub, with everything that explains how you can leverage this function. Just let me walk really briefly about how I designed it. Essentially, I want to be able to generate a room with a specific number of size and generate a specific number of shapes within: spheres, cube, the density, the noise percentage, and the level. This is then going to be leveraged to determine the room boundaries, the floor, the ceiling, the walls, 1, 1, 2, 3, 4, and then after that, the shapes, the random shapes, the cubes, the random cubes, and some additional random horizontal planes for tables, shapes, you name it. And then after that, the noise. So this is a large function. But normally, if I'm good at coding, this is what you can expect. This is the room that you have. And if I were to rerun it, you see that you have random elements that are generated a bit everywhere, but the wall and the ceiling don't vary too much, but we can make that vary based on the room size, of course. So already at this stage, this is marvelous. You have a way to generate a single room fully automatically. Let's not stop there. Beautiful. Now we can move and create a custom export function for a PLY writer. If we were to leave it to Open3D, we would maybe be stuck to work only on Python, within Python, and that will be good if you have the ability to work outside Python in your favorite software. So this is the little function that you can leverage to write a PLY with labels. This is important because if you don't use this specific custom export function, this PLY writer that I give you here, essentially you will not have the ability to handle really well the labels that we extract from our various generation. And you can see here that I keep the labels, vertex labels, equal to labels, so that you can leverage that afterwards. This is that simple. I have vertex x equal, vertex y equal, vertex z equal, and so on. And then after that, I will write to a file on top of which I have a header, and I write in binary format with these bytes writing line per line. So this is that simple. Now, if I do that, I have output scalar. Let me execute that. Let's also explore stage 10, saving with Open3D. And now, if I check on my folder, I have output scalar that I can drag and drop here, and you see that it's working. Funnily enough, I did not implement it a way to just in here take in the scalar as a way to visualize the various colors, but it's there. Trust me, if you were to open that with Cloud Compare, for example, you will have the ability to change that to scalar. But I want to show you another possibility. It's a dirty trick, is actually pass the label and match that to the color map and use Open3D to export the PLY with XYZ RGB. And this is what I wrote here. and I will name it output color. So if I do that, now I open my shape generator, I have output color, and I could then kill that and take my output color, drag and drop, and you see that you have the various colors. You can also be a bit better with the visualization, but everything is working really nicely. It's almost like a little old school video game for the ones out there that are old enough to remember how pixelized it was all the time working around these various game designs. All right, so enough digression. Let's now move on to the final stage. Now we can go on to stage 11, generating room scenes. This is where the power of automation shines. Imagine that now the human effort that you will need to generate 2 rooms or 2 billions is the same. The only thing is to make sure that you can tie down all the elements to have a hand on. And this is also an opportunity for me to share that you don't need the latest, fanciest AI system to do generative systems. Here, this is a generative system that just leverage prior knowledge about data, algorithm, coding, and sensor at large. These are the on top domain knowledge expertise that you can inject to tie that to a specific application that you have in mind. And again, these are the kind of new approaches to coding that you can have before moving on to building something that is a bazooka to kill a fly. If I can have this expression in English. So what I do here is generate multiple room scene and save them as PLY. So you can see that I will have a room size that is really randomly taken between 5 and 15, 5 and 15 for width and length, and the height I vary that between 2.5, which is the normal size of a room, and 4 meter if you are living in a castle. And then after I give also samples for all of my elements, sphere, cubes, point density, and so on, so that I can have something that is generated automatically. And if I generate the room, I would output 3. You can see here that I have already tested, and here number of scene. If I were to put 15, that will not take a lot of time. You see generated 15 rooms. And I also have the ability to see more or less the label counts. This is what I do to understand and always profile what you're generating. So undefine 412 points, plain, and you have that for all of your little generation. And finally, going on to visualizing outside of Python. So now, if I open my folder, you have output room 3, and you have 15 synthetic rooms. And I could drag that and drop it. Let's try it, actually. This is a great test for my little software. I don't know if it can handle some... Yeah, it can. We just don't have the colors. This is where maybe Cloud Compare will come in handy. And you can see that you have all your synthetic rooms, and they are all different, and they vary based on the parameter that we gave to the room. So now that Cloud Compare is almost open, let me just take all of my PLY. Here I don't, yeah, they are not colors, but it's okay. And you will add a Scala field and take in the label, okay? And normally you see that all of them are good to go. I will just move them here. And yeah, this is your synthetic point cloud. This is another one. This is another one. This is another one. This is another one. And this is perfect because you have some basic feature, X, Y, Z, and you have a label. And from there, it's up to you to leverage all the knowledge that you had through the various tutorials that I gave you to extract features and to build detection or perception system, or to go really, really, really deep beyond that. This is not the end. We can go further and explore what you can do with that and what are the current research directions. Now let me bring you onto 3 great tracks that I'm currently experimenting with. These come after you having maybe played with it, replicated, and then extend what I gave here. And then from there, I have 3 main tracks that I'm currently exploring that actually leverage this approach. The first one is generative adversarial network. You can use this kind of deep learning architecture to give a bit more texture to the way you generate synthetic data, something that is maybe closer to what we will have in the real world. This is something that you can do with that. The second element is physics simulation. What about injecting constraints that are really much stronger than just generating things with no relationships and topology? This is also something that you can extend with the third type of experiment that I'm doing, rules with 3D scene grammar. This is something that is not super novel, but you have now ways to leverage new definition of rule and grammar with AI systems. So this is also super interesting. And finally, what will be the 3 logical next stages that I can propose to you? First off is going onto the GitHub repository. So if I click here, normally you see that I created this GitHub repository. You have everything in it, all the setup, all the documentation, how to get started, and so on. I took some time to do that, so this should be helpful. Then after that, if you want to move your expertise a tad more like better, I'm losing my English, go with the 3D data science with Python. This is the most overall book that you can have. This is a fantastic reference to have on your desk to make sure that you have something super relevant written by a human for humans, guaranteed without AI. And finally, you have the 3D Segmentation OS course. So this is really, if you are serious and you want to span off and go into the top 1% of developer creator and create innovating product using all of this algorithm and 3D data pipeline and workflow. I leave it to you here to check out what you can build with 3D Segmentation OS. I finished for me, and I hope this helped you a lot. Have a wonderful day and see you very soon. Bye-bye.